All right, so this is going to be a pretty straightforward lab where we're going to test the pH of several different salts that are undergoing hydrolysis, and it's going to allow us to determine the Ka. So we are going to be using a pH probe. We're simply going to test a bunch of different solutions with the pH probe. It's going to give us a pH value. From the pH value, of course, we can get the concentration of H+, and the concentration of all solutions we're testing is going to be 0.1 molar. So that's going to enable us to determine equilibrium concentrations and thus determine the Ka value. All right, so I've plugged in my pH probe, and one of the first things that I should do is calibrate the probe. And this is generally something we need to do because the probe sits for a long period of time in storage, and it's really only used during one time of the year, towards the end of the year, because that's when the acids bases unit is. So to calibrate, just need to tap on the meter, click calibrate. Yes, I want to calibrate now. And so I have two different solutions here. I've got these standardized buffered solutions, and I'm just going to swirl the probe in this first solution and wait for the live voltage to stabilize. And when it does, I'm going to enter in what the pH value of the solution is. Now, these buffered solutions are engineered to maintain a steady buffer or steady pH. So it looks like it's set there. And this is 4.0. And we're going to keep that value. All right, so I'm done with that buffer. And whenever we use a probe, we always rinse in between. So you should have a rinse beaker, deionized water, before we go ahead and place this in the pH 10 buffer. So let's swirl this in here, wait for that voltage to change, and hold steady. Well, anyways, I can type in what the pH is, and we're gonna keep it. All right, I've entered both of my values, rinse my probe, and now we're ready to test. All right, so we're just gonna see a series of solutions being tested. One thing I wanna point out though, is that I mentioned that I had a beaker of deionized water as my rinse. Now with these pH probes, the way that they're designed, they're not going to function well in low ion concentrations. Since this is deionized water, it's got a very, very low ion concentration, which means it's, right now you're looking at the screen and you might think it says a pH of 10.36, even though this is water. The pH is not really 10.3. It's because it's not able to accurately read anything when there's not enough ions present. But that's not going to be an issue once we go into solutions, because all of these solutions have lots of ions present. So what I'm saying is ignore the pH of the probe when it's in the rinse beaker. Okay, so this first solution that I'm going to test here is sodium dihydrogen phosphate solution, NaH2PO4. These solutions are all 0.1 molar. The probe has a glass bulb inside of it, and so I got to be sure not to clank it too hard against the beaker, otherwise I'll actually crack the probe and, well, then it won't work. So it seems to be holding steady right around here. I do not need to record or graph anything on the actual LabQuest. I'm just going to record the pH wherever it seems to stabilize. It seems to like 4.66, so we're going to call it 4.66. All right, so the next solution is sodium carbonate. Looks like it likes it around here, 12.3. 12.3. We'll just call it 12.34. Next solution is sodium acetate.
Seems to like this region, 7 points. It's still fluctuating.
We'll call it 7.6, 7.62. Next up, we have aluminum chloride.
Seems to like it here. We'll go ahead and call it 3.0. Too early.
We'll just call it 3.09. Okay, so the next solution is sodium
Sulfates. I'm not quite sure.
Let's go with 7.06. All right, next solution, copper 2 nitrate.
All right, we're going to go with 3 points.
We'll just go 3.88. All right, next solution is ammonium
Chloride.
All right, so we're gonna go with 6.25. Next solution is zinc chloride. We're gonna go with 5.29. Okay, next up, potassium phosphate.
Ooh, this could be the winner. How high will it go?
All right, we're gonna call it 13.36. Next solution, calcium chloride.
get this to settle exactly at 7.
That's good enough. We'll go with 6.98. Next solution, sodium bisulfate.
Oof. This one could be our lowest. Seems to not want to go below 1.51. So we're going to call it 1.
We'll call it 1.5. We'll call it 1.51. All right, and our last solution is going to be ammonia, NH3. This one's not dancing around too much. We'll just call it 10.59. All right, so let's talk a little bit about hydrolysis and how you're going to use this in this lab. The word hydrolysis means the splitting of water. So ions that can cause water to split, and the result is something that is acidic or basic. So first, let's talk about cations. Cations can be acidic. So for example, the ammonium ion, NH4+, in the presence of water, it can actually lose one of its hydrogen atoms bonded to it, and when it does, the hydrogen is transferred to the water, and that results in ammonia, NH3, and H3O+, which is what we call hydronium. H3O+ is what results whenever we have acids form. Now this particular reaction is not splitting water, but water is involved in the process of forming an acid. A little bit more complicated are transition metal ions like the copper ion. In this case here, we show the copper 2+ ion interacting with 4 water molecules. This forms a complex. And if you remember from a complex, it's when we have 4 ligands attached to a central ion. So this is a drawing of the hydrated copper ion. We see 4 water molecules and we show their lone pairs. The bond that holds the ligand to the central ion, this is a coordinate covalent bond, right? Both of these electrons in this bond were provided by water, because you know the original shape of water has 2 bonds and 2 lone pairs. So one of the lone pairs is being used to bond towards the central atom. And what happens is the hydrated copper, one of the water molecules, one of the bonds that holds a hydrogen is destabilized and the hydrogen pops off. When the hydrogen pops off, you no longer have 4 complete waters. You have 3 waters and the remains of that 4th water. And that's why the formula changes, because you can't write it as H2O4 anymore. You don't have 4 waters, you have 3 and what's left over. So that looks like this. This particular water molecule here, this hydrogen popped off and it was attached here. So here it is. The bond here is weakened, the hydrogen gets pulled off, and the result of it being pulled off is that it floats away, and now we have 2 lone pairs on that water, whereas originally we had the 1 lone pair and the bond. So the number of waters that attaches is called the coordination number, and the coordination number is typically twice the charge on the metal ion. So being that the charge is 2, the coordination number is 4. Now, if this were an ion with a +3 charge, which we commonly see, so for example, aluminum with a +3 charge, the coordination number would not be 4, it would be 6. And the aluminum in place of copper would have 6 waters on it, not 4, plus the charge would be different. The charge would be +3. When you start with 6 waters and one of the waters breaks, it results in 5 waters and an H+. So be mindful of the charge. The most common transition metal ions that we see that are acidic are the 4 cousin alpha ions: copper, zinc, aluminum, and iron. Copper and zinc are both +2. Aluminum and iron are both +3. If cations can be acidic, then anions can be basic. And when we say anions, we could also include amines lumped into that group as well. So an anion like sulfite, SO3 2-, in the presence of water, the sulfite will attract and draw the hydrogen off of water. And the result is we have a protonated sulfite, and the result is that water is now hydroxide. And if you remember from our basic definitions from Unit 3, hydroxide, a base is something that produces hydroxides in solution. So negative ions will undergo essentially the same process, but not all negative ions. You need to understand what ions will actually do something and which ones won't. Inert ions do not split water, and they're going to be neutral. So examples of the inert ions are any conjugates of strong acids. So if you recall your strong acids, HCl, HBr, HI, HNO3, HCl4, HCl3, right? So they're conjugates. These ions here are all neutral. They will not interact with water in a way that produces hydroxide. Conjugates of the strong bases are neutral as well. So the conjugates of the strong bases are the lithium ion, sodium, potassium, calcium, strontium, barium. These other alkali metal ions and earth metal ions as well, but these are the most commonly seen, and therefore these are the ones that will pop up the most. There are two examples of anions that are acidic that you will need to know, and they are bisulfate and dihydrogen phosphate. Even though they are negatively charged, these particular ions will be able to lose their proton to water and thus form hydronium. The pH equations are going to be necessary in order for you to find the concentrations of either the H+ or the OH-. Now, because in this lab you are being given the direct pH readings, you can find the H+ by simply taking 10 raised to the negative pH. This is a negative logarithmic relationship, and this works for both H+ and it works for OH-. But because we did not read POH, we read pH. So if you need to find the H+ concentration, you need to first find the pH, and then from the pH you can get the POH, and once you have the POH, you can take the 10 to the negative POH to give it your hydroxide concentration. Kw is the bridging relationship. Since Kw is the dissociation constant for water, H+ times OH- at equilibrium is equal to 1 times 10 to the -14th. If we took the negative log of all the values here, that gives us pH plus POH equals 14. And so that's how we're able to kind of go back and forth depending on which data you've collected. Once you have your concentrations of either hydroxide or hydronium, depending on whether you have an acid or base, you can then work on your ice table so that you can find your equilibrium concentrations and find your values for Ka or Kb. So your typical generic example is going to look like this. Whatever base we have, all of the solutions had the same initial concentration, which is 0.1 molar. And so with the pH that you were given, let's say in this instance, the pH was 11.5, because you know the sum of pH and POH is 14, we know the POH is 2.5, because 14 minus 11.5. If we know the POH, we can find the OH- concentration. Once you have the OH- concentration, that is the concentration that exists at equilibrium, because when we took the pH readings, the solutions were all at equilibrium. So that would give us this value here. So this is the equilibrium concentration of hydroxide. So that would go right here. And because the mole ratio is 1:1, that would also go here. So if that was the rate of change, then for your initial concentration, we would deduct that from the initial concentration of the base to give us our equilibrium concentration of B-. So in effect, we have 1, 2, 3 values. We can go ahead and plug them in and find our Kb value. Now this was an example of a base. If this were an example for an acid, it would not be POH that you're worried with. It would be pH that you would take and turn into H+, and you would complete the Ka table and expression that way. So you have to be mindful of what is the solution that you're using. Is it registering as basic or acidic? Because that changes which variable you plug into the ice table.
I want to open this. Merry Christmas, Muffin.
Their pupils are all dilated.
That's when I turned it on.
Muffin.